Hello and welcome to Leetcodes. Today we are going through Leetcode problem number 1277. Count square submatrices with all ones. You're given a binary matrix with m rows and n columns. Each cell is either 0 or 1. Your task is to count how many axis-aligned square submatrices consist entirely of ones. A square submatrix means any contiguous k times k block inside the matrix for any side length k greater or 1 whose every cell is 1. Let's see what the problem is asking us to do. 1. Look at every possible square size, 1 times 1, 2 times 2, 3 times 3, up to min mn. 2. For each size, scan the matrix and find all k times k blocks that fit. 3. Check if all cells inside the block are 1. 4. Sum the counts across all sizes and return that total. Now let's walk through some of the examples. Example 1. 0, 1, 1, 1. 1, 1, 1, 1. 0, 1, 1, 1. We can see that 1 times 1 squares of 1, count the ones, 10. 2 times 2 squares of 1, 4 such blocks. 3 times 3 squares of 1 block, rows 0.2 calls 1.3. Total equals 10 plus 4 plus 1 equals 15. Example 2. 1, 0, 1. 1, 1, 0. 1, 1, 0. We can see that 1 times 1, 6 ones. 2 times 2, 1 block top left at 1, 0. 3 times 3, none. Total equals 6 plus 1 equals 7. Constraints to consider. One reasoned is equaled n, 300, O times min min or even O times min min m min passes comfortably. Cell values are 0 or 1 only. Here are some clarifying questions you might think of asking. Do squares have to be axis aligned? Yes, this is standard for submatrices. Is a 1 times 1 cell considered a square? Yes, it counts if the cell is 1. Are overlapping squares allowed? Yes, we're counting, not selecting disjoint sets. What's the largest possible square? At most min mn. Is the sum possibly large? Max surrounds sim m minus k plus 1 n minus k plus 1, but fits in 32-bit int for 300 times 300 since values are small. Typical solutions use 32-bit. Some hints to consider. 1. To have a k square of ones ending at cell I, j, you must also have k minus 1 squares of ones ending at I minus 1, j, I, j minus 1, and I minus 1, j minus 1. This suggests a min of 3 recurrence. 2. If you know the largest square of ones that ends at each cell, summing those sizes directly gives the total number of all 1 squares. 3. Any 0 at I, j implies no square of ones can end at I, j. Let's see the naive, brute force, intuitive approach. Try every top left corner and every side length, and check each cell inside the candidate square. Time, OMN s cubed, with s equals minim of mn. Because you check OK squared cells for each size k over OS sizes per position. Space, O1. Thoughtful. It's time to think of something better, like using 2D prefix sums. Pre-compute a 2D prefix sum so you can get the sum of any ki's k block in O1. If the sum equals k squared, the block is all ones. Time, OMN, to build prefix, plus OMNS to test all sizes, OMNS. Space, OMN. Still not optimal, but much better. Now let's look at the optimal DP. Classic approach. Let dpij be the size of the largest all ones square whose bottom right corner is ij. Recurrence, one indexed notion for clarity. If matrix ij equals 1, barrier ij equals 1 plus minimuf dpi minus 1j, dpij minus 1, dpi minus 1 j minus 1. Else, dpij equals 0. Then the answer is sum of all dpij. Time, OMN. Space, OMN, or ON with a rolling 1D array. Let's see why DP approach works. dpij counts how far a square can extend ending at ij. It's limited by its top left and top left neighbors. Summing all sizes at all ends directly counts all valid squares of every size. Complexity summary for each approach. Brute force checking cells. Time O m pi n pi s cubed. Space O1. Prefix sums. Time O m pi n pi s. Space O m pi n. DP 2D. Time O m pi n. Space O m pi n. DP 1D rolling row. Optimal. Time O m pi n. Space O n. The idea is to maintain a 1D array dpj representing the previous row's dp values for column j, i.e. up. As we sweep row by row, we update dpj to become the current row's value. Keep prev diac to hold the old dpj-1 from the previous row, i.e. top left. For each cell ij, one indexed for explanation, let up equals dpj, value from previous row, same column. Let left equals dpj minus 1, already updated for current row. Let diac equals prev diac, previous row, previous column. If matrix ii1, ji1 equals 1, then dpj equals 1 plus min up, left, diac, and add dpj to the total. Else, dpj equals 0. Before moving to the next j, set prev diac equals up. Store the old up for the next step. This yields the total count in a single pass, with O of n extra memory. Let's look at the Python code implementation. dpj holds the previous row's value until we overwrite it with the current row's value. dpj-1 is the current row's left, already updated in this iteration. Prev diagnostics preserves the previous row's dpj-1. We accumulate total by adding each dpj because dpj equals the count of squares ending at ij across all sizes. Python complexity O of m time n time O of n space. Now it's time to code up in Java. The indices are shifted by 1 to simplify boundary cases, keeping dp0 equals 0. dpj before update is up. dpj-1 after update is left. Prev diag is top left. Add dpj to total to count all new squares ending at ij. Java complexity. OMN time, ON space. Finally, here are the key points to understand. Understand dpij as the largest square size ending at ij. Sum of all dpij values is the answer. Update order matters. Left is current row, up diag are from previous row. Time, OMN. Space, ON. If you find this helpful, please like, share this problem with your friends, and subscribe for more.